University. Today I'm going to talk about reduction of multisymplectic manifolds. Let's see. And so what I'd like to do in this talk, or very brief talk, is first to give just a tiny bit of background on the question and some of the material. Second, to describe and outline the classical symplectic reduction theorem. And then third, and lastly, to explain my proposed extension of the classical symplectic reduction theorem to the multisymplectic context. And so all of this material, well, okay, all of the material in the third section is based on a very recent paper of mine, Reduction of Multisymplectic Manifolds, published last month. Background. So to start with some preliminary remarks, very, very generally, we might say that reduction is just any sort of procedure that starts with a large space, M with some geometric structure X, and then by a process of restriction and quotienting, we obtain a smaller space, M reduced and X reduced. So this is sort of the most general scheme that a reduction procedure might be expected to satisfy. So the classic reduction theorem, or the classic reduction result, is the Marsden-Weinstein-Meyer symplectic reduction theorem, which we'll talk about in the next section. And then reduction theorems are just completely prevalent in symplectic adjacent fields. So this includes, for example, contact reduction, co-symplectic, polysymplectic, Poisson, Courant, quasi-Hamiltonian, etc. However, it came to my attention that there hasn't been a multisymplectic reduction extension of the Marsden-Weinstein-Meyer symplectic reduction theorem. I became aware of this through a survey article of Gerald Marsden, Alan Weinstein from 2001, where they indicate this this sort of gap in knowledge, as well as a more recent review of Manuel de Leon from 2018, where multisymplectic reduction is identified as being a interesting unsolved problem, or interesting open question, unresolved in the field of symplectic reduction. So, okay, now I'd like to describe and I'm watching the time, I'd like to describe the classical symplectic reduction theorem. First of all, I'd like to establish some conventions regarding our notation and terminology. So M will always be a connected smooth manifold. G is always going to be a connected Lie group. Xi and zeta will always be elements of the Lie algebra of G. Likewise, lambda and tau will always be dual Lie algebra elements. And then given a dual Lie algebra valued differential form mu on M and a Lie algebra element Xi in G, we'll use a subscript to denote the fiber-wise contraction of mu with Xi. So this expression here indicates a differential form on M. And heuristically, we might think of this as constituting the Xth component of mu. And then what I'd also like to do is to identify this sort of mathematical principle, which comes up a lot in differential geometry, but which I've never seen given a name. And in fact, I've never seen even identified as a result. It's sort of a well-known principle, but for pedagogical purposes, it will be helpful for us to name it so that we can, because we're going to refer to it throughout. So I'm going to call this the action descent lemma. And it says that given a free and proper action of a Lie group G on our manifold M, and a G invariant and G horizontal differential form alpha. So recall that G horizontal means that alpha vanishes along the fundamental distribution or on the fundamental distribution associated to the action of G. Then alpha descends to a unique differential form, alpha reduced on the quotient of M by the action of G. And moreover, if alpha is closed, then alpha reduced is closed. So this is, in some sense, the key lemma for both of the results that we'll talk about. All right, and so then a very quick review of symplectic manifolds. So first of all, we'll fix a smooth manifold M, And we say that and so then a symplectic structure on M is just a two form, which satisfies two properties. First, omega, the two form, is non-degenerate in the sense that for all tangent vectors, all non-zero tangent vectors X on M, the interior product of X with omega is non-vanishing. So equivalently, this says that the interior product with omega establishes a vector bundle isomorphism between the tangent bundle of M and the cotangent bundle. And then the second condition is just that omega is closed. And so maximally briefly, Alexander Kirillov identifies three sources of symplectic manifolds. These are the primary sources. So they are phase spaces, complex algebraic manifolds, and coadjoint orbits. Right. So we get some very interesting structure on this space of, or very interesting interaction between functions and vector fields on symplectic manifolds. Namely, there's a map. We obtain a map from smooth functions f, which we might informally associate with classical observables on M, to symplectic vector fields x, which we might associate with symmetries of M. So just recall that a symplectic vector field x is one for which the flow of x, for which the flow of x on the transformation of that induced on the symplectic structure omega preserves omega. And this assignment is characterized by the following equality. And in this case, we say that X is a Hamiltonian vector field for F, or is the Hamiltonian vector field for X. It's unique. And F is a Hamiltonian function for F. And then when X possesses an associated Hamiltonian function, we say that X is a Hamiltonian vector field. All right, so then it's a small step from this notion of Hamiltonian dynamics to Hamiltonian actions. So in order to specify a symplectic action of a Lie group G on our manifold M, we could instead describe the induced infinitesimal action on the level of Lie algebras. And so here it's important to recall that we're assuming that everything is connected. So in this case, we send a Lie algebra element Xi to the fundamental vector field on M associated to Xi. And then here I'm using the negative sign convention so that we have a Lie algebra homomorphism. And then so we can do that in the smooth setting. We don't need any extra structure. But now we can avail ourselves of this assignment of Hamiltonian functions to lift the assignment of fundamental vector fields to the space of observables. So now we're going to send a Lie algebra element Xi to a smooth function f, the associated Hamiltonian vector field of which is the fundamental vector field of Xi. And then when this is possible, and there's some fine print, we say that the action is Hamiltonian. So that is the idea of the moment map, namely that we want to describe a collection of symmetries in the guise of a Lie group action in terms of the assignment of Hamiltonian vector fields. So more formally, we're naturally led to define or to construct a G star valued smooth map mu, which satisfies the condition that, or subject to the condition that, the contraction, the fiberwise contraction with the Lie algebra element Xi yields a function, a smooth function, the associated symmetry of which is the fundamental vector field of Xi. And then we want this diagram to commute in the category of Lie algebras. So there's so of course there's a Poisson bracket on C infinity M, about which I will say nothing, but that will be an important condition later on. And then all of this structure taken together, that is a symplectic manifold M omega with a collection of symmetries G and the associated observables mu, is said to be a Hamiltonian G space. And so this is the sort of the structure, the context that we want to extend to the multisymplectic setting. All right, so now we're in a position to say what we mean by symplectic reduction. So symplectic reduction takes two inputs. First, it takes a Hamiltonian G space that is a symplectic manifold with a Lie group action of G and a moment and an associated moment map mu. And then it also takes a parameter in the dual Lie algebra of G. And so we define the reduced space M sub lambda, that's the reduction parameter there, to be the lambda level set quotiented by the lambda isotropy subgroup of G. And then the Marsden-Weinstein-Meyer symplectic reduction theorem asserts that if the lambda level set of mu is smooth, and if the lambda stabilizer subgroup of G, if the action of that stabilizer subgroup on the lambda level set is free and proper, then, and I'm going to jump down to the picture here, then the restriction of the symplectic structure omega to the lambda level set descends to a unique symplectic structure on the reduced space. So we can always pull back a differential form to a subspace, but it's not always the case that that restricted differential form then descends to anything under a quotient. So this is essentially the content of the symplectic reduction theorem. It says that not only does it descend, but it descends to something that is itself a symplectic structure on the base. The proof of the symplectic reduction theorem is very surprisingly straightforward. It comprises two steps. First, we apply the action descent lemma to the subspace or to the lambda level set quotiented by the lambda stabilizer subgroup, and that gives us the existence, uniqueness, and closedness of what is now just a closed two form omega lambda on the reduced space. And then we invoke a linear symplectic reduction lemma in order to conclude that that closed two form on M is non-degenerate and thus is a symplectic structure. So two steps. So now what I'd like to do is to sort of reformulate this idea of reduction, or to kind of look back at what we described, to extract a kind of a heuristic approach to reduction, which we can then apply to a more general setting, in particular the multisymplectic setting. So in this way, the first thing that we did is to describe a collection of symmetries on M in terms of the additional structure inherent in the symplectic form. So that is manifested in the moment map mu, or that's realized by the construction of the moment map mu. The second thing that we, a second sort of step that we might identify in this procedure is to pick out a distinguished reduced space. So we might say that that would be reduction at the parameter 0 in the dual Lie algebra. And then third, we can exploit the ambiguity in the construction of the moment map. So we can exploit or leverage the ambiguity in the choice of the moment map in order to obtain not just one reduced space, but a parameterized family of reduced spaces. So then that gives us, so this takes a form of taking the reduction of not mu, but mu minus lambda. So we're assuming this is another moment map. So this only works for suitable lambda, of course. And then that gives us the reduction of lambda at the parameter, I'm sorry, the reduction of mu at the parameter lambda. Okay, so this is the last slide of the for the symplectic setting. And so now what we're going to do is we're going to apply these ideas to the multisymplectic case. So multisymplectic reduction. So a quick review on multisymplectic manifolds. Again, we're going to fix a smooth manifold M, and as a introduction or a reminder, I'll say that a k-plectic structure on M is a k+1 form omega that satisfies similar conditions to the symplectic case. First, omega is non-degenerate in the sense that for all non-zero tangent vectors x on M, the interior product of x with omega is non-zero. So this is equivalent to having, or this is to say that in the interior product with omega yields not an identification, but an inclusion of vector bundles of the tangent bundle on M into the kth exterior or kth level exterior algebra bundle for the cotangent space. And then second, we want omega to be closed. So two things here to note. First, the one-plectic structures on M are precisely the symplectic structures. That is, when k is equal to 1, this is the definition of a symplectic form. Second, I'll just indicate that, by the way, so some of the motivation, or maybe the primary motivation of multisymplectic geometry, is that it arises as a natural framework for classical field theories. Okay, and so now we're going to sort of develop a theory, or a framework for multisymplectic geometry that parallels almost, or as precisely as possible, what we saw in the symplectic case. So again, we have a map from observables to symmetries, but now our observables are no longer smooth functions. They're k-1 forms on M for which there exists some vector field X, which bears this which bears this relation with alpha. It's no longer the case, additionally, that all k-1 forms have such an X. So those that do, we say are, we'll call them Hamiltonian k-1 forms. And these, the vector fields on M, which have, which lie in the image of this map, are, we'll call Hamiltonian vector fields. And then it's straightforward to show that Hamiltonian vector fields do indeed preserve the multisymplectic form omega. So in contrast to the symplectic setting, there are now two natural brackets that we might define on the space of observables. First, and the one that we'll use, is a pairing between two Hamiltonian k-1 forms alpha and beta, which is given by the infinitesimal variation of beta along the symmetry associated to alpha. So that's a Lie derivative along the Hamiltonian vector field for alpha of beta. And so this turns out to be a what's called a Leibniz bracket. It satisfies the Jacobi identity, but it's not necessarily antisymmetric. And then there's another bracket, which I won't go into, but which I think is more common actually in the field, which bears I think a closer formal similarity with the definition of the Poisson bracket in symplectic geometry. But I'll note that both of these definitions do extend the symplectic Poisson bracket, and neither of them is a Lie bracket. They're both actually equal up to a de Rham co-boundary. And then, okay, so then additionally, the map from this assignment of Hamiltonian vector fields is a homomorphism of Leibniz algebras. So that's straightforward. So now we again want to construct a moment map, and the idea once more is to describe the symmetries encoded in by an action of Lie group action of G on M in terms of the assignment of Hamiltonian vector fields. So we're naturally led then to define the moment map as being a dual Lie algebra valued k-1 form which satisfies the condition that when contracted, when fiber-wise contracted with the Lie algebra element Xi, yields a Hamiltonian k-1 form, the associated Hamiltonian vector field of which is equal to the fundamental vector field associated to Xi. So this is a precisely analogous construction. And then now, because we don't have a Lie bracket on this space of Hamiltonian k-1 forms, we want this this diagram to be commutative in the category of Leibniz algebras. Okay, and then all of this data taken together constitutes a multisymplectic Hamiltonian G space. That is a multisymplectic manifold M omega with a collection of symmetries G and associated observables mu. Okay, so that's a kind of abstract, or it's a concept, I think it's a conceptually transparent, but not easy to work with characterization of the multisymplectic moment map. So we can identify two very simple equations, which makes it much more easy to handle. So let's assume that we have a Hamiltonian action of G on M and a G star valued k-1 form mu. We then have two conditions. One is the condition that the contraction of mu with the Lie algebra element Xi is a lift of the assignment of fundamental vector fields. That's encoded in this equation. And then second, the Leibniz algebra homomorphism condition is equivalent to, well, literally it's this first equation. And then using the definition of the Leibniz bracket, we obtain this equivalent condition here. So those are so these are the two equations that tell us when mu is a moment map for the action of G. Okay, so then given a Hamiltonian G space and an arbitrary k-1 G star value differential form on M, we might wonder, when is mu plus phi itself a moment map? That is, the question is, how can we vary mu and retain the property of being a moment map? Well, I'm running a little bit low on time, so I'll just state that from the Hamiltonian condition, it follows that phi has to be closed, and from the Leibniz algebra homomorphism condition, it follows that phi itself has to satisfy that homomorphism condition. So I'm going to move quickly through this slide, I think, but the idea here is that the Leibniz algebra homomorphism condition for phi, or for any dually algebra valued differential form on M, can be restated in terms of a stabilization property of phi under the induced action of G on phi. In particular, phi satisfies the Leibniz algebra homomorphism condition precisely when phi is preserved by the action of G, or the natural induced action of G on the space of dually algebra valued differential forms. So this is actually an extension of the equivariance condition from the classical geometry of the moment map. Okay, so now, rather than, as we did in the previous couple of slides, rather than considering a family of moment maps shifted by phi, so mu shifted by phi, and reduction of those family of moment maps at zero, we're instead going to reframe this as having a fixed moment map mu, and now a family of levels, and we're going to discard the condition that the action of G must preserve phi. We'll account for that later, and then we'll just and then we'll define a reduction at at mu equal to phi. So now we have to say what we mean by a phi level set. It's just the equalizer on M of mu and phi. That is, the phi level set of mu consists of those points on M at which mu is equal, at which the value of mu is equal to the value of phi. So now multisymplectic reduction comprises two inputs once again, our multisymplectic Hamiltonian G space and our reduction parameter phi. And the reduced space is defined in an analogous way to the symplectic case. It's the phi level set of mu quotiented by the phi isotropy subgroup of G. And this is the main theorem, namely that if the phi level set of mu in M is smooth, and if the phi isotropy subgroup of G on the phi level set is free and proper, then then the restriction of the multisymplectic structure to the phi level set of mu descends to a unique closed k+1 form mu phi on the reduced space. We don't have non-degeneracy, so it's and in fact it's almost never not. It appears to be almost never non-degenerate. So the proof is extremely straightforward, and analogous to the symplectic case. We first apply the action descent lemma to the induced action of the phi isotropy subgroup of G to the phi level set of mu, in order to establish the existence, uniqueness, and closedness of the reduced k+1 or reduced k+1 form omega phi on M phi. And then we don't do anything because we don't have non-degeneracy. There's no, in contrast to the symplectic setting, there's no linear multisymplectic reduction theorem, which would provide such a non-degeneracy condition. And so that's proof outline. The proof itself is extremely straightforward. I'll show it in 2 slides. It comprises 2 steps. First, we need to show that the phi isotropy subgroup of G does indeed preserve the phi level set. And then second, we just need to show that the restriction of the multisymplectic structure to the phi level set is actually G invariant, or I'm sorry, is actually G phi invariant and G phi horizontal. So the first step, it's quite straightforward. First note that the phi level set of mu is the vanishing set of mu shifted by phi. And then we're going to invoke the alternative characterization of the characterization of the Leibniz algebra homomorphism condition in terms of isotropy subgroups to conclude that for all, or to infer that for all Lie algebra elements xi and zeta that preserve phi, we have the Leibniz algebra homomorphism condition for those phi preserving Lie algebra elements, and then so on this side we have first order variation. We have information on the first order variation of mu minus phi in the directions encoded in the symmetries encoded in the action of G phi. On the right-hand side, we have 0th order information. This is data about the values of mu minus phi, and then along the phi level set of mu, well, this is by definition 0. So that is to say that mu minus phi contracted with any Lie algebra element whatsoever, that as long as xi preserves phi, that first order variation is going to be 0. It's going to vanish. So this means that, and because we're assuming connectedness, this means that G phi preserves the vanishing set of mu minus phi which is equivalent to saying that G phi preserves the phi level set of mu. And then the second step and the last step, we need to show that the restriction of the multisymplectic structure to the phi level set is invariant and horizontal. Well, invariance is immediate because Hamiltonian actions, as we saw at the beginning of this section, are automatically multisymplectic. And it's horizontal by a slightly more involved series of steps. So because the isotropy subgroup preserves the level set, we can move the interior product through the restriction. Then we rewrite this interior product in terms of the Hamiltonian condition on mu. So this is the familiar moment map condition. These two terms are equal. Now mu, so on the phi level set of mu, well, mu is equal to phi, so we can replace mu by phi. And then phi is closed. Our reduction parameters are closed, so this term here vanishes. And that gives us G phi invariance. And that's it. That's the entire proof. So thank you very much for your attention.